Hi everybody. In today's video we're going to talk about some gas laws lab techniques and some gas laws lab procedures. So the first technique I want to talk about is the process by which we collect a gas over water. In the previous video I explained that this is a common way of isolating a gas. When we collect a gas over water, we're typically going to use a trough of water and some sort of a collection vessel, sometimes called a eudiometer. And you can see I'm taking a graduated cylinder here. I'm going to fill it entirely with water, letting the air escape, and then I'm going to invert it. And you can see, just like the principle that's involved with how a mercury barometer works, the water does not fall out, and that's because atmospheric pressure is preventing the rise in the water level in the tub that would be required for this water to be displaced. So here, with this water in the graduated cylinder that's inverted in place, I can go ahead and introduce a gas to this tube and collect it inside that eudiometer. In this case, I'm going to use just this dust-off can, and we've done a lab before in this class where we actually can determine some properties of this gas and whether or not it behaves ideally by introducing the gas very gradually until I get the water level to be equal to the water level in the tank. Now that looks like I've got it just about right, and you can see I have about 80 mils of the gas that I'm interested in here. However, because I collected the gas over water, I not only have whatever gas is in this container, I've also inadvertently added some water vapor. If you imagine being a tiny little person inside that container, it would probably be pretty humid in there, right? Well, that's because of water vapor, and we need to take into account the partial pressure of water vapor if we want to consider the total pressure in that container. Now I've zoomed in on the eudiometer for a moment to illustrate another important principle. Right now you can see that the water level inside the eudiometer is lower than the water level inside the tank. Now if I lift this up, the water level inside the eudiometer is higher. So at what point in time is the pressure inside this container greater than, less than, or equal to atmospheric pressure? For instance, right now, when the water level inside the eudiometer is lower than the water level in the tank, what is a greater pressure, atmospheric pressure or the pressure inside the container? Consider which pressure is greater as who's winning, which is more successful in lowering or depressing that water level. The pressure inside that container is so great that it's able to lower that water level to an even lower position than atmospheric pressure is. So this is higher than atmospheric pressure right now. Conversely, when I lift it up here, you can see that the pressure inside the container is actually less than atmospheric pressure because atmospheric pressure is being more successful than the pressure inside the container. That means if the two water levels are equal, then the pressure inside the container is equal to atmospheric pressure. And that's an important principle when we're collecting gas over water in a eudiometer. We want to measure the volume, which looks in this case to be about 95 milliliters, when the two water levels are equal. At that point in time, the pressure inside the eudiometer is equal to atmospheric pressure. So we now have 95 milliliters of gas, and if I hold the two water levels equal, the total mixture of gases has a pressure, is exerting a pressure of 1 atmosphere. If the current atmospheric pressure is exactly 1 atmosphere, or 760 millimeters of mercury. So I want to explain how Dalton's law of partial pressure will be valuable here if we want to know what the partial pressure of just the gas that I collected is. Remember, this contains a mixture of gases, not only the gas that I collected, but also water vapor. I can look up the partial pressure of water vapor online or in the back of the reference book, and I find that the partial pressure of water vapor when the water is only at 20 degrees, or when the temperature of the mixture of gases is only 20 degrees Celsius, is only 20 millimeters of mercury. So if the total pressure in here is 760, and only 20 of that is due to water vapor, then the partial pressure of the dry gas alone is 740 millimeters of mercury. But if this water were at 60 degrees, the partial pressure of water vapor is 150 millimeters of mercury. And that would be a significant difference, since 760 minus 150 is 610 millimeters of mercury. At a higher temperature, the partial pressure of this gas would be significantly lower in that mixture. So sometimes we want to know what the partial pressure of just the gas of interest is, or the dry gas, in other words, without including the water vapor, and we'll need to use Dalton's law of partial pressures to do that when we're collecting a gas over water. So we're going to apply those principles of collecting a gas over water to a different lab procedure. I'm going to carry out a reaction between hydrochloric acid, which is 6 molar in this case, which is pretty concentrated, and magnesium ribbon. And you know that that's a single displacement reaction. Magnesium, Mg, and HCl is going to produce hydrogen gas. So that's the gas I'm going to collect in a eudiometer. This time, I'm not going to collect it in a 100 milliliter graduated cylinder, but instead I'm going to use a proper eudiometer. A eudiometer, that's spelled E-U-D-I-O meter, is a lot longer and we can get a more precise measurement of volume. Now, how am I going to carry out a reaction in this vessel and ensure that all the hydrogen gas that's created in that single displacement reaction is actually trapped inside of here? Our solution is going to be to hold the piece of magnesium ribbon in a copper cage in the bottom of this container and allow a small volume of concentrated hydrochloric acid to slowly mix through water, descending and reacting with the magnesium ribbon. When the reaction occurs, all of the hydrogen gas, we hope, will actually be displaced upward into the tube. Now I've measured a small amount of this magnesium ribbon, and the exact mass I'll display on the screen later so that you can use that number for calculations. This is going to be a stoichiometry lab as well. We'll be able to predict exactly what amount of gas this small amount of magnesium should produce with the hydrochloric acid and calculate our theoretical yield. Then, when we actually trap that amount of gas inside this eudiometer, we'll see what our actual yield is, and we can calculate percent yield like we've done before. The first thing I'm going to do is wrap up this little bit of magnesium ribbon inside a copper cage. I'm going to take a little bit of copper wire, which will not react with the acid, and I'm going to wrap the magnesium with the copper wire. I'm making a little cage so that the magnesium can't fall out, but the hydrochloric acid can still react with it. This takes a little bit of dexterity, but I think that will do. Let me give you a closer look. The next thing I'm going to do is to take this apparatus and I'm going to suspend it just a few centimeters deep into the eudiometer. I'm going to use a rubber band to keep it in place. Let me show you what that looks like. Now, I'm going to take this out for just a moment because I haven't yet added the small amount of acid that I was going to rely on to react with this. I'm going to use 10 milliliters of 6 molar hydrochloric acid, and that is enough so that the hydrochloric acid will not be a limiting reactant. It will be an excess reactant. In other words, all of the magnesium ribbon should react. I'm going to use a pipette and pipetter to add those 10 mils of hydrochloric acid to the eudiometer. And now I'm going to fill the eudiometer with water. When I fill the eudiometer with water, I'm going to do it gradually because I'm relying on the fact that hydrochloric acid is much more dense than water. And if you look at the molar mass of hydrochloric acid and the molar mass of water, that makes sense. They're not entirely immiscible, of course, so I don't want to mix it up too much. However, it is sufficient so that essentially we have the 10 mils of hydrochloric acid at the bottom of this tube and almost nothing but water in the top 3/4 of the tube. The fact that the top 3/4 of the tube are mostly water is going to allow me to put my finger on the top safely, just long enough to invert the tube into the tub of water. Now I'm going to fill this tube all the way to the top, even to the point where it is overflowing. And again, the very bottom of this tube contains concentrated hydrochloric acid, but the entire top 2/3 or 3/4 or more is just water. Now that I've done that, I'm going to set that bit of magnesium ribbon in there, and I'm also going to attach that apparatus with the rubber band that I showed you before. So I can show you again what that looks like. Now, with my finger placed on top, I'm going to invert this into the tub of water and clamp it in place. Almost immediately you can see the hydrochloric acid starting to descend. You can maybe see the hydrochloric acid looks a little bit different. You can see it's starting to mix with the water, and slowly it's beginning to descend. Soon we'll see some bubbles as it starts to react with the magnesium at the bottom. So now you can see that the reaction has already started and is happening pretty rapidly. The hydrochloric acid has descended all the way to the bottom, and it's reacting with the magnesium, and all the hydrogen gas that's being created is being bubbled up to the top. We only have a few milliliters of hydrogen gas collected so far, but once the reaction is complete, we'll see if the amount of hydrogen gas we actually generate, our actual yield, is close to our theoretical yield. So you saw the reaction taking place at 10 times speed for a moment, but now it's done. And the total volume of gas we've collected is 54.6 milliliters. Now, you're going to be asked to do some calculations to determine whether 54.6 is greater than or less than the theoretical yield you calculated. And also to consider a few other things. 54.6 milliliters of gas is our actual yield, but we are not measuring at STP. So one consideration is whether or not that difference between lab conditions and STP conditions accounts for any discrepancy between actual and theoretical yield. Why are we not at STP? Well, first of all, STP means 0 degrees Celsius or 273 Kelvin. This is not only room temperature to begin with, but it's an exothermic reaction, and so the temperature of this gas is certainly higher than standard temperature. How about pressure? Well, we've got two things to consider here. Number one, you should be able to determine whether the pressure inside this container, which is a mixture of gases, is greater or less than atmospheric pressure. Remember, the water level here is higher than the water level in the trough, much higher. And I don't have a trough that's deep enough to get these two water levels equal. So what effect would that have on the difference between actual and theoretical yield? Is this pressure lower than atmospheric pressure or higher than atmospheric pressure? In addition to considering whether the pressure of the mixture of gases is higher or lower than atmospheric pressure, we also have to consider that the pressure of the dry gas alone, in other words, just the hydrogen gas, would be less than the mixture of gases pressure together. So I would have to take the total pressure in the container, even if it were atmospheric pressure, and then subtract the partial pressure of water vapor in order to know the partial pressure of the hydrogen gas alone. Now, we could use the combined gas law, P1V1 T2 equals P2 V2 T1, to correct for the difference between lab conditions and STP conditions. But instead of doing that calculation, I want us just to consider qualitatively whether or not lab conditions and STP conditions difference would account for the difference between actual and theoretical yield. So that wraps up this discussion about these gas law lab techniques and lab procedures. We'll see you next time.